Okay, this is section 2.1, linear and quadratic functions with modeling. First thing we're going to talk about is polynomials. We'll call this P of x because it's a polynomial instead of f of x. The key to a polynomial, they take this basic form, some number times x to a power, plus they're kind of using this notation, just another term, another number. That number could be 1, we don't always write it then. That number could be 0. I might not have this term in the polynomial. Okay. Plus minus. The key to polynomials. The exponent or the n must be a positive integer or a whole number would be another way to say that. Probably the easier way. So 0, 1, 2, 3, 4. They cannot be negative. Okay? So we'll go through a couple examples in a second. A sub n, that first coefficient, standard form must be in descending order of powers. So if there's a fifth, that's 5, 4, 3, 2, 1. This last one here, a0, is like an x to the 0. Anything to the 0 power is 1. So this really doesn't need to be here because it's just times 1. A sub n is known as the leading coefficient. That's going to be important terminology. A sub 0 equals the constant term. Okay. The degree of the highest exponent is known as the degree, or the number of the highest exponents. So degree n here, or if it's x to the fifth, and that's the highest exponent, that would be degree 5. Names for different degrees. Degree, well, I'm going to write it out in kind of a table here. Name. Degree 0 is known as constant. That's a horizontal line. Degree 1 is known as linear. Degree 2 is quadratic. You should be familiar with all of these so far. Degree 3 is cubic. Degree 4 is quartic, not quadratic. Quartic is degree 4, quadratic is degree 2. Degree 5 is quintic. Degree 6 is 6th degree. Degree 6 and higher, we just say 6th degree. Okay. Gonna put a couple of examples of some functions and we'll decide if they're polynomials. Okay. So the first one, polynomial. My power is a 2. My power here that's not written is a 1. And this is an x to the 0. Those are all whole numbers. 2, 1, 0 are whole numbers. Yes. This one, I see a power of 2 and a power of 1. The problem is this power of 2 is in the denominator, which makes it a -2 second power. So this is a no. -2 is not a whole number. This one, the square root is the same as the 1/2 power. 1/2 is not a whole number. As soon as one of mine fails, doesn't matter how many other ones are good, it's fails. I'm gonna do a k of x here. This is actually a yes. Pi and square root of 2 are not my exponents. My exponents are 3 and 5. So, yes, this is a polynomial. The coefficients are not what defined as an exponent. Those can be irrational or strange in any way, shape, or form. I guess I did different ones. You can look at example 1 if you want for some other ones. Okay. Example 2, finding an equation of a linear function. So we know this is a function and we know it's linear. We are told these two pieces of information. This may not be the form you're used to seeing them in. But what does it mean? It means f of 1, that means x coordinate is 1 equals 2. I've got a point -1, 2. I've got a point -3, -2. Here, I'm reversing my stuff. I don't know why it erased that much. There we go. So to write the equation for a line, what do? Start by finding the slope. Remember the slope formula, y2 minus y1 over x2 minus x1. Pretty sure that's somewhere in your Bible. Doesn't matter which y's of which as long as I match. So the -2 here and the 3 must go on top of each other. The +2 and the -1 minus, I write minus negative, and then I change them both to a plus. -2 minus 2 is -4 over 4. Which can reduce to -1. Oh, what a nice, easy slope. I like to use the point slope form here to write my equation. I'll pick, say, the first point. Y minus, the y coordinate is 2, -1, x plus 1. So it's minus -1 becomes the +1. And this is a valid answer. I might write it like this, not write the 1, but I would most likely leave it like that. The answer key is probably going to put it in slope-intercept form. And part of the reason you put it in slope-intercept form, another valid answer would be using the other point. Both of these will convert to the same slope-intercept form. So I'm distributing, and then I add 2 to both sides. And either one you do, you should have seen that before. If you don't believe me, convert the other one on your own, but you'll get y equals -x plus 1. I don't care which form you give it in. This is valid to me. That's going to be valid. This is valid. If it's one of these on the test, I have all the answers that it could be. And if you come up with something else, if it's valid, I'll still give it to you. I'll check. Okay, so that's pretty straightforward. I'd like everybody to look at page 175. And we're going to talk about linear correlation and modeling linear graphs. Okay. So correlation tells me how well does data fit a line. I'm going to draw some things that are kind of close. That one they call strong positive. Positive or negative has to do with the slope. Does the slope of what we're going to start calling a regression line, you might have called it a line of best fit in the past. Does it fit? Is it positive slope? These are positive. This is strong. The data fits tight to the line. This is weak. I'm going to do some negatives. This one over here is kind of weak. This one is pretty strong. Yes, I did intentionally reverse those. If your line looks like your line that would go through it is perfectly horizontal. Oops, that wasn't perfectly horizontal. We usually call that no correlation. And your calculator is going to calculate what's known as the correlation coefficient, R, for you. But you have to know what it means. R is a kind of ugly, complicated calculation that you can learn about in statistics, but it's always a number between -1 and 1. -1 means every point is dead on my line. Makes perfect line with a negative slope. +1 means makes perfect line with positive slope. Hint, positives are positive slope. Doesn't matter how steep the slope is. That has nothing to do with the correlation. It's how tight do they fit to the line. Okay? R near 0 is weak correlation. And by near, I mean really less than half or less than -half. So I'm actually going to go absolute value of R. The sign tells me whether it's positive or negative correlation or positive or negative slope. Close to 0 or close to 1 or -1 means strong. Oops, those are not absolute values. So the near 0 equals weak. Absolute value near 1 equals strong. I'm getting ahead of myself. Something like absolute value near like 0.6, 0.7 is moderate. 0.8 even is moderate. It's not super strong. So modeling and predicting demand. Okay. We have a data table on 1675. I want everybody to enter that into your graphing calculator in your lists. I'm going to get it. Okay, so I just entered the data on my calculator, and I'm going to show you how to do that here. So we'll go out of there and go from the beginning. So I press the stat button here. I hit enter on the edit. Enter into 1 and 2. Never hit delete. If you want to clear out your list, scroll up to the top and hit the clear button. Do not hit the delete button. It will literally delete the list from your thing. There's a way to get it back, but it's a little bit of a pain. So I've got all the data in the list. If you don't have that, pause the video, enter it into your calculator right now. I'm going to quit out of this now And I'm going to show you how to add so you get the correlation coefficient. Some of you might have done this already. I press the second button of 0 as catalog, and it defaults to alpha, so I'm going to press the one with the green D here. And that's going to take me to D quickly. I'm going to scroll down to diagnostic on. I'm going to hit enter. It'll say done. Now, when I calculate my regression line, start calling it a regression line, it will show me an R value and an R squared value. We'll cover R squared, what that means at a different time. So to calculate it, I press the stat button again, scroll over with the arrows to calc, and I'm going to go to linreg AX plus B. Kind of wish it was at MX plus B, but AX plus B works. There's a linreg A plus BX. It's the same thing, but they switched the order. So make sure you pay attention to this. X list and Y list. L1 and L2 is where I entered my data. If I need to change that, L1 is second function of 1. L2 is second function of 2. L3, second function of 3. Frequency list, I don't think we will use this year. So X list and Y list should be whatever you set them as. Sometimes you'll need L1 and L3 because you'll have the same X coordinates for multiple different lines. Store reg EQ stands for store regression equation. We're going to put it so it shows up in our Y equals and shows up on our graph. We do that with the vars button. You scroll over to Y vars, you select function and Y1. Okay? Now scroll down to calculate. There we go. Hit enter. And I now know my equation for my line, and you must write it this way, do not write A and B, is negative 15,358.92 X plus 73,622.5. Again, we've done a bunch of this, but here's my new thing. R is negative 0.98. That says I have a negative slope, which I could tell here from the negative on the slope. But it also tells me it fits a line quite well. We're going to check it by looking at the graph. And we can do that by going to make sure it's turned on. Second Y equals a stat plot. I guess I need to clear some of this off. And I'm going to go to plot 1. I need to turn it on. So I turn it on. Type, this is scatter. That's what we're going to be using most of the year. List L1 and L2 just like I had. I'm going to come over to zoom and go down to zoom stat. Zoom stat will automatically fit my data on the screen. And there it is. That does look like it fits a line pretty well with a negative slope. Okay, back to the whiteboard. So, transforming the squaring function. Talked about graph transformations at the end of last unit. This is EX4. We're going to start with transforming y equals x squared, or f of x equals x squared. We know from our basic functions that that's a parabola. And we're going to do some transformations on it. G of x, actually, let's do a different color. So I'm going to put them on the same graph. Again, a lot of this is going to be sketches, kind of rough sketches. But I'm going to be looking at finding specific points, and I'll number the graph when we get there. So this function, this out here at the end is a vertical shift of up 3. And I'm just going to write up 3. This is reflect over x-axis. For the negative sign. The 1/2 is vertical compression of 1/2, or vertical stretch of 1/2. So what I need to see when I see this graph is going to be that you've gone up 3. It opens down, and it should look wider. I'm not focused on how specifically wider, but it should look wider than the basic one. Okay? That is good enough. That would get you full credit. We're going to look at h of x, which has some other transformations on it. This is left 2, opposite the sign inside. This is down 1. Stretch 3. So this one's going to be, it's going to look narrower because it's stretched vertically, and it's like it's taking each point and pulling it up, which makes it look narrower with parabolas. So here again, over 2, down 1. This point has to be here. It has to open up, and it's got to look narrow. Axis of symmetry. Axis of symmetry here goes right through the middle. We say x equals -2 for that one. The other two are both x equals 0. The maximum is the point at the top here. And it's the y coordinate. The purple one here is a min at -1. Okay, I'm giving the y coordinate. Okay, finding the vertex of a quadratic function. That's not supposed to be there. So, you know, standard form of a quadratic. The vertex can be notated like the coordinate -b/2a and f of -b/2a. What does that mean? Well, let's take a parabola. -3 x squared plus 6x minus 5. For -b/2a, b is 6, so that's -6. A is -3. Oh, that gave me a nice one. 1. My vertex has an x coordinate of 1. To get the y coordinate, I plug that value in. So I'm doing f of 1. Plug it in for x, calculate. Anytime I need to get a y coordinate, I can just plug in my x coordinate. 1 squared is 1. -3 plus 6 minus 5 is -2. And here's my vertex, 1, -2. Okay. So we have 2 different forms of a quadratic. We have vertex form, which is essentially transformation form. They address completing the square. We'll do that later in the year. And we have standard form. From vertex form, we know the vertex is located at HK. That's very handy. Standard form. Y equals ax squared plus bx plus c. You're pretty used to this form. C is the y-intercept. That's kind of handy. You can do negative b over 2a. If you need to convert standard form to vertex form, let's take this one that we had here. A is the same. I found my vertex, so I'm just going to plug that in for H and K. Now we're in vertex form. Okay. So we're going to talk about predicting maximum revenue. So example 7 here says, use the model y equals negative 15,358.93x plus 70,622.5 that we got in example 3. Okay. To develop a model for weekly revenue generated by a donut-shaped oat breakfast cereal sales. Determine the maximum revenue and how to achieve it. So revenue can be found by multiplying the price per box by X. So this was the function for price per box. Revenue then, and actually I want to call this P of X so that I can use a little bit of function notation and simplify my writing. Revenue then, R of X, is going to be P of X times X. Or if I multiply all of this by X, what happened? I lost a lot of stuff there to the eraser. I get negative 15,358.93x squared plus 73,622.50x. If I want to find my maximum revenue, I just need to find the vertex. I could do negative b over 2a. I think I'm going to use a graphing calculator because that's also a valid option. So I'm going to go over to my graphing calculator and I'm going to graph that. I'm going to go to y equals. I'm just going to clear all of this out. First thing I'm going to do actually is turn off plot 1. I do that by taking my arrow, scrolling over plot 1, highlighting it, hitting enter. I'm going to clear all of these graphs out. And I'll type in the slightly rounded off one. Okay. Now I'm going to have to find the window that's going to work for this. I'm guessing my maximum revenue, I was in the data went from like 0 to 3 points or 2.4 to 3 point something. I think I want to, well, actually, we're going to widen this out to 0 to 5. My Y min, I'm going to set as 0. My max, since I multiplied it by X, I think I need to go higher than this 41,000. I'm going to go like 200,000. This is kind of a guess. Y scale, I do not want to be 1. Usually I do something that's like 1 power of 10 less. Let's see what that looks like. Oh, hey, I see a max. I don't care that it's not near the top. It looks different than the book, but I see the max pretty clearly, so that's good. So I'm just going to go find maximum. Second trace, again, the calc menu. maximum. Find something on the left for a left boundary. Find something on the right for a right boundary. And I get a maximum at 2.39 here. So what did the question ask me? The question actually asked me to determine the maximum revenue. So the maximum X, which I got to look back at the problem to see what it was talking about. The maximum price per box is basically $2.40 per box. The context of this problem was the more I charge for the box, the less I'm going to sell. The maximum revenue is going to be $88,226.27 or 72 cents. Yes, I did round off the price per box. It's just kind of how you have to do it. Because you don't charge 239.6735 cents. We are going to finish with a free fall problem. I'm going to use pretty basic free fall in this. And you're going to use this free fall equation. It is in your Bible. S of t or h of t. They use S in the book. I might have used h in the packet. I'm not sure. Equals gt squared plus v0t plus s0. Okay. They also give you a velocity equation in this unit. Negative gt plus v0. Think in the packet, I filled in values of g. G in metric is 9.81 or 9.8. We're going to use 9.8 in this class. So half of 9.8 is 4.9 t squared plus v0 t plus initial height. And v0 stands for initial velocity. This is metric. In feet per second, it's 32 feet per second squared. So half of 32 is negative 16. That's how these values are coming in. The acceleration due to gravity. So this is in metric or meters. This is in feet. So modeling with free fall. We got a data table. To write models the height and vertical velocity of a rubber ball. Then use these models to predict the maximum height of the ball at its vertical velocity when it hits the face of the CBR. So the data table here collected in Boone, North Carolina, about 1 kilometer above sea level, using the calculated based Ranger, a 15-centimeter rubber air-filled ball. The CBR was placed on the floor. I think that's the thing that's capturing it. Okay. So this is just capturing some data. We've got our data table on 181. We're going to put that into our calculator to find the free fall. Okay. So we're going to go back to our lists. Nope, not second stat. I just want stat. Edit. I'm going to scroll up here and I'm going to hit clear. Clear it out. I'm going to enter all my data. Yeah, I'm not entering the zeros at the end. They are necessary for significant digits telling me how accurate this thing's measuring it. I accidentally put the thing in the wrong spot. I've seen that happen in class before. If you have one data point that doesn't fit everything else, you probably hit a wrong button or missed a decimal. If your answer doesn't make sense with one of these, check that you didn't miss a decimal. This device that they are using is measuring really accurately. And I did enter that one correctly, and it should take it correctly. It just didn't have enough digits, so it's rounding some of these the last digit. That's fine. I think it knows what the actual thing you entered, though. And I'm pretty sure it will keep that calculation. It just can't show it. Okay. Now I've got this. I don't need to turn by units at only again. It's just staying on pretty much the calculator. If it doesn't, something about it. So to get this, I'm going to go stat calc. I can see from the book that it looks like a parabola, so I'm going to go down to quadratic regression. I'll store my reg EQ again, just like I did before. Bars, y bars, function, y1. I'll go down to calculate. It calculates it. It does not give me an r, but it gives me an r squared, which is very close to 1. This fits the model really well. I'll go turn my stat plot back on. I didn't change anything, so I can just go to y equals and turn it on. Zoom. If I hit the 9 button, it'll jump right there. And there's my data to the point. Okay. My equation. Oops. I didn't look long enough. We'll calculate it again. I don't really need to do star regression equation again because it already did it. So I know my equation here is y equals negative 4.676 x squared plus 3.758x plus 1.045. If I want to write the velocity equation, I know g. This tells us about negative 4.9. There's a little air resistance throwing it off. My initial velocity is this. So I can write a velocity equation. Right, gt, negative gt. Sorry, I did this backwards. Times 2. I need to multiply that by 2. Because that one was 1. This was 1/2 g. Times t plus 3.758, which gives me negative 9.352 t plus 3.758. And that is my velocity equation. I got my values from the regression, and then I figured out what they were using my equations. Let me go back to the whiteboard. Using this equation, I knew that 1/2 was the negative 1/2 g was the negative 4.76. So I found out what g was, so I could plug it into the velocity equation. V0 just translates back and forth. Okay, that's it for this lesson.